Okay. It's connected across a battery of E volts with internal resistance R ohms. Very good. Then the power in watts in the external resistor is if E and R are fixed. R is the variable. In other words, it should be written P of R. What is the maximum value of the power? What is the maximum value of the power? So I have the privilege here, in a way, or happy that I'm given the function. I don't have to create the function. There is no worry about finding the function here. I do have the function, and I'm asked to find its maximum. Okay, so what do I do first? Very good. So P prime of R equals. This is a ratio. The top has the variable, and the bottom has the variable. Since E squared is a constant, I am not going to involve it in any way, shape, or form. So the top prime is R prime, which is 1, times the denominator. So it's R plus R squared minus the top times the denominator prime, which is 2, times R plus R times the inner function prime, which will be 1. I don't even have to write it. Everything divided by R plus R to the 4th power. Do we agree with this step? Any questions on this? Are we okay? Yes? Okay. Next step, of course, I will do what? Remember the two major keywords. What are they? Correct. Always factor if you can. It will make your life easier. So I factored out, I see I have two terms here, and they both have R plus R, right? So then I took one away from the first quantity, and I have R plus R. So one from here and this. So then minus twice R. Is this okay? Of course I will get rid of one R plus R. And then I have E squared, and this is little r minus uppercase R over R plus R to the 3rd. Do we agree with this step? Yes? Okay, very good. So I'm done with the first derivative. Now what? Exactly. P prime of R set equal to 0. When is the ratio 0? When the top is 0. But E squared is a constant. So when R minus R is 0. So obviously I'm solving for uppercase R. Little r is a constant. Uppercase R is the variable in the problem. So this is it. I found a critical number. But I don't know if this critical number turns into a max or a min. I have to show you, I have to convince you that indeed R lowercase r will turn into a maximum. So I have to do this. R is the variable in the problem. P prime of R and P of R. Like we do with everything, right? So I have to show that the signs change accordingly and create a maximum at that value. So I have the little r. I know that this is 0. And I want to be able to say that this is the local max. But I'm not able yet. So I look at the expression representing the first derivative. What is this? Always. R is a constant, lowercase r is a constant. We are told these are ohms. Okay, so then the sign will be only given by this expression. It's a linear function with a negative slope. That's the sign for a linear function with a negative slope. What type of typical situation is this? Is it typical for or typical for a maximum? So when uppercase R equals the lowercase r, the external, what was it r? The internal resistance, then the power is the maximum. What is the maximum? If I'm asked to determine that, what is the maximum? And I am. All I have to do is replace uppercase r by lowercase r. So I have P of lowercase r. I have E squared times r over lowercase r plus r, which is twice r squared. So this will be E squared times r over 2 squared, which is 4, r squared, which is r squared. And all I have to do is simplify one of those. So E squared over 4r. This is the local max. And should be put right there under R0 and for P of R. Very good. Perfect question. Thank you. I was going to show you something like that anyway. But very good. Anything else before we go back to that cost function for the box without a lid from last time? Have you worked on anything else that you need help with? Yes, please.
Can we ask you a question for another section?
Oh, any section, anything, yes.
On page 317, number 65, I think it was.
317, 60.
No, sorry, I wrote that down wrong.
That's
41.
okay.
Sorry, I crossed out.
That's okay. It's not 65, but it's 41.
41.
That's fine. 317. 317, 41. Very good. Excellent example. So y equals arctangent e to the x. Arctangent e to the x. Very good. So the question here in this section is asking us to show everything and graph it. Okay, perfect. First I have to start with the domain of this function. I see two functions, right? I see e to the x inside arctangent. Correct? Okay, perfect. Let's start with the inside. The inside function, e to the x. What is the domain of e to the x? Is it a friendly function? Does e to the x create any problems? All real numbers, friendly function, defined everywhere. So for this one, the domain is everything. Now I have to think about, and remember the graph. This is very important. This is the graph of e to the x. Now let's think of the graph of arctangent. How does arctangent look like? Exactly. What is the domain of arctangent? Indeed, very good. So arc tangent x has domain all real numbers, And let me refresh your memory. This is the graph. It has a horizontal asymptote y equals pi over 2. It has a horizontal asymptote y equals negative pi over 2. We graphed this function several times before. And this is the graph. Excellent. So then I know the graph, the domain of y. What is the domain of y? I'm going to call it f of x as well. Can anyone give us the domain? Very good. Very good. Do we understand how we determine the domain? We looked at the inside function first. It was all real numbers. Then we looked at the outside function. No restrictions for either one of them. Therefore, y has domain all real numbers. We accept that? Perfect. Okay, so now I have to try to see a few things. Find a few things. Number one, the end behavior. I need to find the limit here, and I need to find the limit here. And then I have to find x and y intercepts. That's everything I can find about the function from the function itself. X and y intercepts and limits. There are no vertical asymptotes. If the function were not defined on all real numbers, then I would have looked here as well with limits. But since the function is defined everywhere, then I only have to find this limit, and if it has x and y intercepts. That's it. Okay, so let's start with the limit. Limit as x approaches negative infinity from arctangent e to the x, and also limit as x approaches infinity from arctangent e to the x. Perfect. So now I have to first think of the graph of e to the x. So again, I start from the inside as x approaches negative infinity. I have the graph in my head, but let me look at it again. As x approaches negative infinity, e to the x will approach. Excellent. Do you all see that 0? You agree? As x approaches negative infinity, the function values get closer and closer to 0. Acceptable? Yes? Now I want to find arctangent 0. I have the graph in my head, but I'd rather look at it. So arctangent 0 is? Do you all agree with 0? Right? Okay, perfect. So I have 0 here. In that case, I know something about this function. What do I know? That y equals 0 is horizontal asymptote. I make myself a note. Y equals 0 is a horizontal asymptote. This is the end behavior. When x approaches negative infinity, the function approaches a number. That means it must be a horizontal asymptote. Agreed? Okay, perfect. Let's check the other side. Again, I have to start from the inside, e to the x. I look at the graph again. When x approaches infinity, e to the x, when x approaches infinity, e to the x approaches infinity. As x approaches infinity, e to the x approaches infinity. Agreed? Okay. So then I will say that this approaches infinity. Now, I want to find limit of arctangent when this expression approaches infinity. So in other words, I want the end behavior of arctangent when x approaches infinity. I look at the graph. When x approaches infinity, arctangent gets closer and closer to. Do you all agree with pi over 2? As x approaches infinity, function values get closer and closer to pi over 2. Good. What does this mean? When x approaches infinity, the function values approach pi over 2. What does this mean? Horizontal asymptote. So y equals pi over 2, horizontal asymptote. We have not seen this type of example before. At one end, it has y equals 0 as the horizontal asymptote, and at the other end, it has pi over 2 horizontal asymptote. So at negative infinity is 0, and at positive infinity is pi over 2. Are we okay so far? Yes? Okay, perfect. So now I'm trying to see if this function has x and y intercepts. So for the x-intercept, I have to set y equal to 0. For the y-intercept, I have to set x equal to 0. Good. So let's start with this one. So I want to find f of 0, which is arctangent e to 0. I should have written 0, not x. Okay, so how much is e to x? 1. How much is arctangent 1? Let's go back to the unit. Careful. I need an angle. Right? So, yes, arctangent 1. So remember on the unit circle, tangent is positive in 2 different quadrants. So I have to give. Right. Now, if we consider arctangent as we normally would, just between these two, I will definitely say pi over 4. So I have 0 somewhere here, and I have pi over 4 here, and I get 0 here. We'll see in a minute what happens if I need to determine more solutions. Okay? Okay, because this is between, so it's 0 here, it's what, I'm sorry. See what I did? I'm talking about the y-intercept and I wrote something else. Sorry. We'll see in a moment if we'll catch any discrepancies in a blink. Once we're done with this and with this, we'll see in a moment if we need to go any further. Okay, so for now, we put pi over 4. Okay, now for this one, y equals 0. Arc tangent e to the x equals 0. Okay, so let's solve this equation. So what should e to the x be? Somewhere between negative pi over 2 and pi over 2, so that arctangent is 0. So how much should I have here? What should this be? Where is, so give me an angle whose tangent is 0, between negative pi over 2 and pi over 2. 0 indeed. So from here, e to the x must be 0. Therefore, x must be Does this have solutions? No. No solutions. E to the x, we know that. Let's look at the graph for a second. E to the x is never 0. The limit is 0, but e to the x is never 0. Good. So there are no x-intercepts. None. So that's all I have from the function, about the function itself. I'm ready to move on to the first derivative. Okay, f prime of x. I have to differentiate arctangent e to the x. Okay, what is the derivative of arctangent? What is the formula for the derivative of arctangent? 1 plus x squared. Very good. So let me write it on the side for you. Arctangent u prime equals 1 over 1 plus u squared times u prime. Very good. 1 over 1 plus u squared times u prime. Perfect. So this will be 1 over 1 plus e to the x squared times e to the x. Good. I found the first derivative. Now what? What do I do with it? What will be my next step? What am I interested in doing next? Finding the critical numbers. Very good. Setting it equal to 0. F prime of x equals 0 means e to the x over 1 plus e to twice x equals 0. When is the ratio 0? Right, but e to the x is never 0. So there is nothing I can do here. No solutions. Now I need to determine the sign of this. What type of number is e to the x? Positive. What type of number is 1 plus a positive number? So then, what does this mean? We have to make sure that these two rows work in sync together, right? So from 0 to pi over 4. Pi over 4 is 3.14 over 4. So approximately 0.785. So this is approximately 0.785. And if I divide this by 2 again, I get 0.3925. Okay. Oh, this was pi over 4. This was pi over 2. They're reversed. Sorry, I wrote them incorrectly. Because I realized, oops, how can it be? This cannot be a bigger number than this because the first derivative is positive all the time, and they have to show that. So this is 3925. Let me erase it. So this is 0.3925, and this is 0.785. 0.785. Okay. I wrote them in the wrong spot. Good. So now,
I'm getting
yes.
pi over 2. I got 1.5.
So did I copy them incorrectly? So pi divided by 2. Oh yes, 1.5. Oops. 1.57. Thank you. Oh, I did. It was that 785. Oh, okay. 785. 0.785. Okay. Sorry about that. So now we are looking at make sure that these two go in sync. Yes, from 0 to 0.78, yes. From 0.78 to 1.5, yes. So it's always increasing. The numbers show that, the sign of the first derivative, and so on and so forth. I'm looking at the second derivative. So I'm going to differentiate to get the second derivative and see if there is anything happening, any inflection point, anything in there. Ready? Perfect. So I differentiate the top and I get e to the x times the denominator and minus. So e to the x times this prime, which is e to 2x times 2 over 1 plus e to 2x squared. One more time. So I'm differentiating this. E to the x prime is e to the x times the denominator minus the top function times the denominator prime. When I differentiate this, I get e to 2x times the inner function prime, which is 2. Do we agree with this? Okay, perfect. So now I have 1 plus e to 2x squared. I will definitely factor out e to the x because it's in the way. Now let's see what is left. I have 1 plus e to 2x and minus 2 e to 2x. And I have e to the x, and this is 1 minus e to 2x over 1 plus e to 2x squared. Do we understand the algebra part? No. These are not the same. Good. So now I'm going to set the second derivative equal to 0. This can never be 0. The denominator does, I don't even want to talk about. So what can be 0 here? Very good. So then this means that 1 raised to 2x equals 1. So 2x must equal what for this equation to have a solution? Indeed. So therefore, x equals 0. So when x is 0, the second derivative is 0. Now, I hope you agree that the sign of all this expression is definitely, as we discussed before, positive. So I have to see what happens here. Well, no problem. So let's say I plug in 5. 1 minus e to the 10th. E to the 10th is almost 3 to the 10th power. Huge, negative, definitely negative. No problem there. Now I'm going to plug in negative 10. 2 times negative 10 is negative 20. But e to negative 20 is almost 0. So this is positive. E to negative 20 is 1 over e to the 20th power. And that's almost 0. Is that clear? Yeah. Let me write it. Yes, you're right. So I plugged in negative 5. So I'm looking at e to 2 times negative 5, which is 1 minus e to negative 10, which is 1 minus 1 over e to the 10th power. And this is so small that this is approximately 1. Because this is roughly 3 to the 10th power, which is huge. And 1 divided by huge is 0. And definitely not more than that. That's all I was interested in, the sign. So therefore, on this sign, this is positive. So now I'm ready to graph. I have to show two asymptotes. I have to show the asymptote of 1.5 to the right-hand side. So if this is 1, I'm going to have to show this. Y equals pi over 2. Then I have to show this is an overkill, there is no need. But I have to show y equals 0 to the left-hand side. I have to show 0, 7.8. 0, if this is 1, 7.8, I'm going to say is this point. And now I'm ready. The function is always increasing, opening upward. From approaching the asymptote of 0 to this point. This is not a maximum. It continues to increase. This is a point of inflection. 0, pi over 4 or 0, 0.785 is an inflection point. So it increases from approaching the asymptote till this point, where it changes concavity, opening downward, but continues to increase towards the horizontal asymptote towards infinity. Very interesting function. Thank you for picking that. So this is the function f of x, arc tangent e to the x. There are no news whatsoever, but let's check it with the graphing calculator. Calculator cannot give us anything new. So arctangent, so the inverse of tangent of e to the x. No, I didn't mean that. E to the x. Close the parentheses. The calculator will not give us all the asymptotes. Or 0 it will because it's the x-axis. But I have to punch in pi over 2. It will not give it to us. Now the viewing window, I'm going to say between -6 and +6, scale of 1. Y minimum, -2 is good enough. And Y maximum, I know it doesn't go beyond 0.7, so I'm going to say 4 with a scale of 1. And now I want the graph. Here comes the graph, crossing at 0.7, approaching y equals pi over 2. Here's the horizontal asymptote at -infinity only. Here's the horizontal asymptote at +infinity only. So opening upward, inflection point, opening downward. Always increasing, knowledge domain. Very good example, wonderful. Good, next question please. Next question. Is there anything else, or we go back to the cost function? So we can finish that one. Yes, is there a problem? Yes. So we have the equation x minus this equals 0. Is that correct? Okay, the same thing. Okay, x cubed minus 2 equals 0, which is the same thing. If we take this cube, that's fine. That's the same thing. Good. So we want to solve the equation, right? So when this is our function, that's f of x equals x cubed minus 2. Right? Good. So if you remember how we approximate, so we have f of x plus a little bit is approximately f of x minus f of x plus a little bit, which is dy, or f prime of x dx. Okay, so we were asked to use differentials. Do you remember? Can I look for a second? I don't want to. So, oh, the Newton's method. Oh, I thought we were talking about we wanted to approximate. Oh, okay. Then we don't need any of this. So remember, the xn plus first iteration is xn minus f of xn divided by f prime of x. Good. So we are looking at this. And we know it crosses, so when we graph the function, right, we know it crosses somewhere between 1 and 2. That part we know. How do I know? Okay, let's do the whole thing. So if we plug in y equals, if we plug in this function, x to the third, which we know it's polynomial, differentiable, continuous, and differentiable everywhere. And by the intermediate value theorem, since it's continuous, if I show, let me put it in first. If I show that it changes sign on a 1-unit interval, then I know that there is a solution there because it's continuous on all the domain. Okay. So then I go to second table. Oh, I have to do that again. Okay, second table. So if I plug in 1, I get negative. And if I plug in 2, I get positive. because I know the cube root is somewhere between 1 and 2. So I will write number 1, function is continuous. F of x, which is x cubed minus 2, continuous on the interval 1, 2. And I can show that f of 1 is -1 and f of 2 equals 6. Therefore, by intermediate value theorem, there exists a solution C in the interval 1, 2, this is a bracket here, such that f of C is 0. So I know, in other words, that there is a root between 1 and 2. Okay, so now I want to use Newton's method to determine that, and we have to establish how many digits we want, what accuracy we want. We want 3 digits, we want 4 digits, 5 digits, so we know where to stop. If we don't have that, or we're not given that, then we don't know when to stop. So it all depends on you how many digits you want. 4, very good. So we want a 4 with the accuracy 4 digits. Perfect. So now it depends on where I want to start. So I know that f prime of x is 3x squared. It doesn't matter where I start. I can start with 1 or I can start with 2, because f prime at 1 or f prime of 2, they're not 0. So it doesn't matter. Which one would you like to start with? So I have to identify x0 is blah. 1. We want to start at 1. Perfect. Then we are going to create this function that I decided to use uppercase F on it as the name. It doesn't matter. You name it as you like. If you don't like this name, just name it Newton's method. Whatever name you want to give it. Then you will say x minus f of x over f prime of x. You put this function in, your Newton's method function, in the graphing calculator. So in y equals, clear, and we have x minus the top, in parentheses please, x to the third minus 2, close the parenthesis. Minus 2, close the parenthesis, and divide by. It is meant, the best idea is to put parentheses on the denominator. You can say, but it's only one term. But if you don't put parentheses, it will only divide by 3 and not by x squared. So be careful. So parentheses 3x squared, close the parenthesis. And this is Newton's method. And I exit from there, go to variables. Go to variables again, call the function. I only have y1. I deleted everything else. And we decided to plug in 1. And now I'm going to copy all these. So x1 then is 1.33. Now x2. I go back to, or just copy the previous entry. That's the best thing to do. And overwrite 1, because we're not plugging 1 again, I'm plugging this number in now with second and answer, and close the parentheses. So now the same function called Newton's method of x will be evaluated at x1. Better? Okay, so now I press enter and I get the next answer, which is x2, 1.263888. They're 5 eighths. Okay? I just recall the previous entry. Now I don't have to do anything, because when I write this again, the calculator will plug in the previous answer, which is 1.26388888, in Newton's method of x.
Wait, how do you do
that? With second and enter. And now I press enter again, And the next answer is x3. And it's 1.259933493. We're not at 4 digits yet, so I will do the same one more time, second and entry, and press enter. And now the calculator will plug in the previous answer, and I'm done, because I see 4 digits already repeated. So I don't have to write x4. So the answer to this, with 4 digits as we discussed, of the approximation of the cube root of 2 is 1.2599. So this is it. Since the next step repeated the first 4 digits, I don't have to consider that anymore. There is no need to go to the next iteration. Are we okay with this so far? So now, if you want, you can check your, so put 2 caret in parentheses, cube root is 1 divided by 3, and let's see if we get this. Of course, as you see, the 4th iteration is 2, 4, 6, 8 digits accuracy. And in this way, we can solve any equation that we could not prior to Calc 1. We had no means. We had no idea how to find the cube root of x cubed minus 2, a solution to that by hand, other than just punching in the cube root of 2 in the calculator. Good. Anything else before we go back to that cost function? Is this good enough? Is this okay? Perfect. Okay. Do you have anything else for me? Other questions? Okay, so let's go back to and finish up this cost function. We determined the function. It was a max-min situation. So now we need to find the critical numbers. So I'm going to copy the function here. Okay, so C prime is 40x. And I need someone to remind us how to differentiate 1 over x.
Negative 1 over x squared.
Very good. Perfect. So it's negative 180 over x squared. Now I need to find critical numbers. So I set this equal to 0. I have to find the least common denominator, which is x squared. I have to multiply this by x squared. So I have 40x cubed minus 180. Do you agree with this so far? We found that the least common denominator was x squared. I had to multiply the top of the first fraction by x squared, so I got 40x cubed minus 180. Everyone with me? Yes? Okay. So now, when is a fraction 0? In only 1 hour, I think I repeat myself like 5 times. Yes. So I have 40x cubed minus 180 equals 0. I'll simplify by 10. And then I'll simplify by 4. So I have 18 divided by 4, which is 9 divided by 2. Yes, I take the cube root, so x equals the cube root of 9 divided by 2. I will approximate this as parentheses 4.5, which is 9 divided by 2, raised to power 1/3. You can do it the way you like. Okay, and this is 1.651, approximately. And I don't remember what was the measurement unit. Anyone remembers? I don't even remember which problem we're doing here with the cost. So x was in feet or meters? Very good, thank you. Perfect. So now, if this is not enough, if I cannot convince you somehow, C prime I don't remember if we were asked to determine the minimum cost. Well, let's find it anyway. So here I have to show that this is indeed giving a minimum. I don't know if 1.651 gives a minimum. So I have to show you that that's the case. So this is definitely a positive number. Now the numerator, I don't know. I'm just going to plug in two numbers. So 1.6, I'm going to plug in 0. It's negative. I'm going to plug in 100. 100 cubed times 40 is way over 180, so this must be positive. And this is definitely a situation for the local min. No doubt that the sign gives a local minimum. Now, if I want to determine the local minimum, I have to go back to the function, the cost function, which was this, and plug in this function 1.651. So I'm going to, okay. So I want 20 multiplied by the previous answer squared minus 180. No, it wasn't minus 180. It was plus. Plus 180 divided by the previous answer. So I got $163.54. $163.54. Were we asked to determine, x, let's find h as well. The height of the box, the dimension. So then h equals 5 divided by x squared. And I'm going to plug in, so 5 divided by the previous, I'm going to redo this 4.5 raised to 1/3. So I get the answer again, the previous one. And then I want 5 divided by the previous answer squared. And that's the height of the box, which is 1.8344. So h approximately 1.8344 meters. So you will tell to the manufacturer of the box, sir, if you want to have the minimum, reach the minimum cost, make sure that you do not make it wider than 1.651 and taller than 1.8344, because then you will exceed the minimum cost. These are the specific dimensions that will cost you exactly 163.54. If you deviate from 1.651 and 1.8344, you're not going to achieve the minimum cost. Any questions? Any questions?